Okay, in the second part of this lesson here, we're going to talk about standing waves in strings. So recall that a standing wave is one in which the wave pattern does not move. If this was animated, you would see these antinodes sort of flip-flopping back and forth between these two positions, but it's not moving in a left to right direction. And these standing waves result when you have two wave patterns that have the same wavelength, same frequency, same amplitude, and they're traveling in opposite directions. Most of the time you will see this when you have a reflection off an object, although like in air columns, you don't necessarily need something at the end to cause the reflection. Recall that there's always going to be nodes and antinodes. So nodes are these points in between where the wave does not actually appear to be moving at all, and the antinodes are where the maximum amplitude is occurring, although it is flip-flopping back and forth. So if you had a string that was vibrating like this, you could actually grab hold of those nodes and you would feel that it's not actually moving at all. These standing waves can appear anytime that there are two waves interfering with each other. So like I said, in the previous lesson, we've been talking about air columns. In this lesson, we're talking about strings that are fixed at both ends. So if you have a string that is fixed at both ends, well, this implies that there has to be a node at both ends, because a node is a point on the wave that does not appear to be moving. So we've got nodes here at both ends. And so these standing waves will, there's several different possibilities for what these waves are going to look like, depending on the frequency. But there are still only very specific frequencies that work. So the fundamental frequency, or what we call the first harmonic, sometimes we write this as F1. So this is going to occur when we've just got a single node at both sides, no nodes in the middle, and as you can see, if we were to extend this wavelength out here, you can see that we fit half of an entire wavelength in here. Versus on the second harmonic here, you can see, well, we can fit an entire wavelength in. We still have those nodes at either end, although in this case we have an extra node in the middle. And so this pattern will continue for all of the higher level harmonics. You can continue up F2, F3, F4. As long as you have a node at either end, you're going to have a standing wave. And this relationship between the wavelength and the length of the string is consistent. Like we showed here, we can fit half of a wavelength in the first frequency. So if we're looking at the first one, we could say that the length of the string would have to be half of the total wavelength. If you wanted to find the wavelength of the second harmonic, well, the length would be equal to 2 over 2, or the length would just be equal to the wavelength. And this pattern continues. So you can sort of generalize it here, where the length is equal to the harmonic multiplied by the wavelength divided by 2. And this is just because of how these wavelengths fit into the string, where there is still a node at either end. We'll go into a couple examples. Okay, in this example, we have a 1.2 meter string that vibrates at a fundamental frequency of 65 hertz. And we want to know what is the speed of the wave through the string. So let's write down what we know. The length is 1.2 meters, and the fundamental frequency, so we'll call that F1, is 65 hertz. So if we recall, if we have a standing wave in a string, well, we need a node at either end. and the standing wave is just going to look like this. We can either think back to what the formula is, or we can kind of derive it ourselves here and realize that we've got half of a wavelength that fits within the string here. So we can write that as the length, which is this length here, is equal to, well, we only fit half of a wavelength in. So the length is equal to lambda over 2. So the actual wavelength itself is equal to 2 times the length, which in this case is going to be 2 times 1.2 meters, is equal to 2.4 meters. And so finally, we're looking for the speed. The speed is equal to the frequency times the wavelength, the universal wave equation here. So this will be equal to 65 hertz multiplied by 2.4 meters. If we calculate this out, we find that this is 156 meters per second, though we only have 2 significant digits, so we should round this to 1.6 times 10 to the 2 meters per second is the speed of this wave in this case. All right, second example here. We've got a fundamental frequency of a string, so we'll call it F1, is equal to 637 hertz. And the length of this string is 27 centimeters. We'll call this length A, because we've got 2 different lengths here that we're dealing with, 27.0 centimeters or 0.270 meters. And we want to figure out what the fundamental frequency would be if the same string was 22 centimeters long instead. So again, we'll write this as 0.220 meters. So this is quite similar to the first example for the first little part of this. What we're going to do is we're going to figure out what the velocity is of the wave. So in this case, we can assume that both of these strings are going to be at the same sort of tension, and so the velocity in the first string we can assume is going to be equal to the velocity of the wave in the second string. So this is kind of the key to making this question work. So we're going to go ahead and figure out what velocity in this first string is. So again, we're talking about the fundamental frequency. So if we draw our little diagram of our standing wave, we've got this where at either node we don't appear to see any movement, and kind of in the middle we're going to see this anti-node flip-flopping back and forth. So again, this part in the middle here, if this is our total length, that's only going to be half of a wavelength. So the length is equal to lambda over 2. So again, lambda is equal to 2 times the length. Call this length A in this case. It's going to be 2 times 0.27 meters. So the wavelength in this first string is going to be 0.54 meters. So therefore the frequency in this first, sorry, not the frequency, the velocity in this first string is going to be frequency times the wavelength. Our frequency was 637 hertz multiplied by 0.54 meters. It's going to give us a velocity of 343.98 meters per second. I'm not going to round or anything yet because we aren't at our final answer, so we'll keep all of our decimals until the end. As we said above, the speed of the wave in the first part has to be equal to the speed of the wave in the second part, so this is also going to be equal to velocity in B. And so now we kind of need to go back the opposite direction. So velocity b is equal to that fundamental frequency of b multiplied by the wavelength of b. Rearrange this. We are looking for this frequency here. We don't yet know what the wavelength of b is, but we can calculate it because, again, we're talking about the fundamental frequency. So up above, we had said that the wavelength was equal to twice the length. So we'll just replace the wavelength here with twice the length. And we know what that length is. So the frequency is 343.98 meters per second divided by 2 times the length of that second string, which was 0.22 meters. Our units cancel out, and we're left with a fundamental frequency of 782 hertz. If we add, say, a part B to this question, what is the, let's say, the third harmonic frequency of the second string? Well, the third harmonic is just going to be equal to 3 times the first harmonic for a standing wave in a string. So in this case, we can just multiply 3 by that 782. So if we want to get the third harmonic showing up here, we would end up with 2.35 times 10 to the 3 hertz would be what the third harmonic looks like. And if we want to think about what this is actually going to look like, well, we're actually going to end up with 2 nodes in between, so it'll look something like that. This would be what the third harmonic looks like.